Forced oscillations and resonance. In this session, we will explore several key topics regarding how systems behave when external forces are involved. We will begin with the basic concept of forced oscillations and define the steady-state conditions that occur over time. We will also examine the mathematical description for the amplitude of a driven oscillator and dive deep into the fascinating phenomenon of resonance. Finally, we will look at some impactful real-world examples where resonance plays a critical role in engineering and physics. We have previously seen that the mechanical energy of a damped oscillator naturally decreases over time because of retarding forces like friction or air resistance. However, we can compensate for this energy loss by applying a periodic external force that does positive work on the system. A common example of this is a damped oscillator being driven by an external force that varies over time. This force is mathematically described as the driving force amplitude multiplied by the sine of the quantity angular frequency of the driving force times time. Here, the driving force amplitude is a constant, and the angular frequency determines how fast the external force oscillates. To understand the motion of such a system, we use Newton's second law to model the object. We account for the driving force, the retarding force, and the restoring force. The sum of these forces equals mass times acceleration. Written out, the driving force amplitude times the sine of angular frequency times time, minus the damping coefficient times velocity, minus the spring constant times position, equals mass times the second derivative of position with respect to time. After the driving force acts for a sufficiently long period, the system reaches a steady state condition. At this point, the energy put into the system by the driving force in each cycle exactly equals the mechanical energy transformed into internal energy due to damping. Once the system reaches the steady state, we can describe the position of the oscillator using a specific solution. The position equals the constant amplitude times the cosine of the quantity angular frequency times time plus a phase constant. It is important to note that in this condition, the forced oscillator vibrates at the specific angular frequency of the external driving force, not its own natural frequency. Additionally, the amplitude of these oscillations remains constant for any given driving force, providing a stable pattern of motion over time. The amplitude of a driven oscillator is not arbitrary. It depends on several physical factors. The formula for amplitude is the driving force amplitude divided by mass, all divided by the square root of a sum of two terms. The first term is the square of the difference between the square of the driving angular frequency and the square of the natural angular frequency. The second term is the square of the quantity damping coefficient times driving angular frequency divided by mass. The natural frequency mentioned here represents the frequency the system would have if there were no damping at all, calculated as the square root of the spring constant divided by mass. As we can see, the resulting amplitude is highly sensitive to both the frequency of the driving force and the amount of damping present. Resonance is a unique state that occurs when the driving frequency is equal to the natural frequency of the system. When these frequencies match, the amplitude of the oscillations increases dramatically, especially if the damping is small. On the graph shown here, we see different resonance curves. For an undamped system where the damping coefficient is 0, the steady-state amplitude would theoretically approach infinity as the driving frequency nears the natural frequency. As the damping coefficient increases, the peak of the curve becomes lower, and the overall shape of the resonance curve broadens, meaning the system becomes less sensitive to the exact match of frequencies. The physics behind resonance is centered on energy transfer. At the resonance frequency, energy is transferred from the external source to the system under the most favorable conditions possible. This happens because the applied force is perfectly in phase with the velocity of the oscillator. Power is defined as the dot product of the force vector and the velocity vector. Since the force and velocity are moving in the same direction at the same time, the power delivered to the oscillator reaches its maximum value. In real-world systems, there is always some level of damping, which acts as a safeguard to prevent the amplitude from growing infinitely and destroying the system. A famous and tragic example of structural resonance is the collapse of the Tacoma Narrows Bridge in 1940. Even though the winds that day were not exceptionally strong, they were turbulent enough to provide a periodic driving force. The frequency of the wind's flapping effect happened to match one of the natural vibrational frequencies of the bridge structure. This created a resonance condition that led to large amplitude oscillations, which the bridge was not designed to handle. Eventually, the structural stress from these massive vibrations caused the entire bridge to collapse into the water below. On this slide, we see two historical photographs capturing the final moments of the Tacoma Narrows Bridge. The image on the left shows the roadway twisting and undulating violently due to the resonant vibrations caused by the wind. The image on the right captures the actual moment of collapse as the center span breaks apart and falls. These images serve as a powerful visual reminder of why engineers must carefully calculate natural frequencies when designing large structures. Resonance appears in many other areas of our daily lives and technology. In electric circuits, components like capacitors and inductors create natural frequencies, allowing circuits to resonate when a specific varying voltage is applied. This is how radio tuning works. You might also hear telephone wires singing in the wind, which is caused by the wires vibrating at their natural frequency. In mechanical engineering, moving parts in machinery can break if they fall into resonance with other vibrating components. Another classic example involves soldiers marching. They are often ordered to break their rhythmic step when crossing a bridge to avoid setting up resonant vibrations that could compromise the structure. To summarize our lecture, forced oscillations occur whenever a periodic external force is applied to a damped system. In the steady state, the system vibrates at the driving frequency with a constant amplitude. Resonance represents the dramatic increase in this amplitude when the driving frequency matches the natural frequency of the system. We have seen that the specific shape and the height of the resonance peak are determined by the damping coefficient. Ultimately, understanding resonance is a critical requirement in engineering and physics to ensure the safety and stability of everything from electronic devices to massive bridges. To wrap up, let us review two important concepts. First, think about the specific physical conditions required for a driven oscillator to reach a steady state. Consider the balance of energy input and energy loss. Second, explain why the power transferred to an oscillator reaches its maximum value exactly at the resonance frequency. Be sure to focus your explanation on the phase relationship between the applied force and the velocity of the object. Reflecting on these questions will help solidify your understanding of how energy and forces interact in oscillating systems.